Hello, welcome back. This is eighth lecture in the series of lectures in dynamics. We already finished kinematics before, and now dynamics. If you recall, we have already completed tension-related concepts. Almost I have covered most of the models that are possible. But what I do at the end of this chapter, probably I'll be doing some miscellaneous models where these are involved and then something else is also involved, okay? Well, as before, let me tell you that you are supposed to subscribe if you and like and share, and I would be very happy if you could do that. And uh, now look at what we have done in that four forces. The four forces, the manifestations of electromagnetic that we took. One was tension, which I did in great detail. Now the next one I'm going to look at is normal reaction or force. Normal force. Actually, its name should have been pressing force. Now, what is this force that you are talking about? Remember, now follow my arguments carefully. Now, you do not get carried away with what the book gives. Whenever two bodies are pressed against each other, either two bodies or two surfaces, etc., the force exerted by one on the other, perpendicular to the common surface, are also called interface. I definitely would like to give you, whenever two bodies are pressed against each other, the force exerted by one on the other, perpendicular to the common contact surface or interface is called normal force. This is given with a symbol here. I purposely wrote this. I want you to understand this concept very clearly. Just because two bodies are in contact force need not arise. I'll just give you an example. For example, you see, this is a duster. Now I am putting it, leaving it. So it is falling down. The surface is in contact with this, but there is no normal force. Okay, this is a very important point. Where does this come from? You see, how does it come? I'll tell you. The reason why I said it should be called a pressing force is based on the example that you saw a little while ago. If you press that duster to the board, then there is a pressing, therefore the force is exerted by the board on the duster, by the duster on the board. Both are present depending on which you consider that you represent there. But it should always be perpendicular to the common surface or interface. Okay? How does this arise from? For example, if you look at any surface, at micro scale, the surfaces, however smooth they appear to your naked eye, when you look at microscopically, that is how the texture or the structure of the surface looks like. Now, both are like this. We don't know. There may be some contact points. There may be, you see, every molecule has a range. I mean, in other words, a molecule within a surface, let us say, about a particular length, maybe in terms of microns or whatever. In 3D space surrounding that molecule, whatever molecules that are coming to that particular surface, imaginary surface, there is an attractive force between the two. Okay? So the normal force is essentially due to intermolecular attractive force. Okay? More the number of contact points, more will be your normal force. Now, this is how it is. Say, for example, I fix this surface. As of now, I can't count the number of contact points. That is ridiculous. You can't say 5, 6, etc. There will be millions or billions also. But for your understanding, I am telling you, supposing if these are few contact points you have. Now what I do, I press this body. What am I doing? I am making more and more points to be in contact. So the intermolecular surface also, intermolecular force also increases. So normal force increases. And it is essentially due to the pressing. So a very important point. So therefore I prefer to call it as a pressing force. Normal force is called because this essentially arises due to the contact, number one. Two, the component of that force is perpendicular to the common surface. That perpendicular or normal, that is why this is called normal. That is number one. Number two, if I take that body, but what is it you have understood from here? If you press it, number of contact points increases and consequently the force also increases. Now, suppose if I take a body, the contact points are at maybe several points. This is a 3D picture I am trying to draw. Okay? And so if this is the surface, that is the surface. There are contact points distributed everywhere. So where does the force act? Everywhere it acts. But when you take an average picture of that, in general, not always. Now, this is where I say you follow my arguments very, very carefully. In general, if no specialities are present, you may take it at the geometric center at which this normal force will act on this body by this surface. You get the point? There may be few more contacts, but less, etc. If you take average, we take as though it is representing the entire force at the center of that contact surface. This is how generally we take it. But now this is an important point. Although while discussing this, I do introduce the concept of torque or the moment of force that I already discussed before also. But again I do it. For example, I am now trying to push this body forward. I'm just trying to do that. There is a possibility that this body may get toppled. For example, this one. Now, if you do it, there is a chance that it may get toppled. Or if it is here. Now, when I do this, you can see it is coming. That means the contact has come to the edge. This is called toppling. Topple, the body is getting toppled. So the whole contact has shifted to the edge. Well, this is the direction of your net force. So the point of application of normal force also gets shifted in the direction of application of net force. I am not taking any other force here in the horizontal. So there is a chance that it will get toppled, right? And then I would say that whenever there is a net force acting on the body, then there is a chance that the normal force may get shifted to the edge of the body. It doesn't straight away go from the center to the edge, just like that. So, if I apply 100 newtons, this is getting toppled, this is getting toppled, I am applying only 50, then it would not go to this, it may be somewhere in between. So, the more the force that you apply, the more is the point through which it gets displaced further and further. I hope this point is clear to you. Okay? Now, I'll just do that. This is where I am applying the force. I am taking this point to be H. This is L. Okay? Now, this is the center. Now, at the center we know if the surface is horizontal, mg acts vertically down on the body. I am putting it. And this is force. Now, n you don't try to draw like that. What you should do, it may probably get shifted slightly. Let us say it shifts by a distance b. Okay? Now, you look at that. Suppose at the center, if I take my axis, I expect the body to turn. For turning, you need a force at a distance from the point or axis that I am talking about. The so-called moment of force. Now, if I take this point, this will tend to rotate the body in this direction. Body is not getting rotated. Body is not getting toppled. But the tendency of that body is to topple it. So, if I say, I told you that what is the magnitude of that moment of force? Magnitude of the force into the perpendicular distance, which is h by 2. F into h by 2. So, this will try to tilt the body, rotate the body in clockwise direction. If no other force were to present to oppose that, then the body could have toppled. So, but here if you see, mg is passing through that point. Remember, whenever the force intersects the axis, it can't contribute to any of your torque or moment of force. So, the only force that can contribute is this. And how does it tend to rotate? In the anti-clockwise sense. What if this is plus, that is minus, is acting at a distance, perpendicular distance b, and there is equilibrium, therefore this is equal to 0. So what is your b? Fh by 2n. Okay, now in the vertical direction, this is not getting accelerated, therefore, in this case, n is equal to mg. Don't take and substitute n is equal to mg everywhere. N differs from case to case. And this is a very wrong notion many students tend to possess. You have to come out of it. That's why I'm going to discuss in great detail this normal force. So, if n is equal to mg, I can write this as so this is the distance to which it will get shifted. Now let me tell you to what is the maximum that it can move. If you don't want the body, to get toppled, your V must be always less than L by 2. Definitely, unless it goes to the edge, toppling doesn't come in. Therefore, this is less than L by 2. In other words, this implies F must be less than mgl by h. mgl by h. If you apply such a force, less than this, all depends on the dimensions, then this body will never get toppled. But what is happening in this direction? This is bound to accelerate. This is bound to accelerate with certain acceleration A. Therefore, F is equal to ma. As simple as that. If you want, you can substitute that and write the whole thing in terms of your acceleration. I'm not taking any complications here. What is happening here? The body is getting translated, isn't it? Translational acceleration is present. So you want translation to take place, not toppling. This is the condition. Suppose when you apply, you go on increasing this force, definitely the body will accelerate. Number one. Number two, it will also have a tendency to topple also. The toppling is in addition to the translation. A point that we will discuss much later, but still at this stage itself I want you to understand while learning normal force. Okay? So if F is greater than this, what we would say, the body not only accelerates, it gets toppled also. Okay? I'll revisit this concept once I discuss friction also. For the time being, I'm sure this is more than enough. So what is it that we have learned from this small discussion? Number one, in the normal circumstances, we take the normal force to act through the center only. But in cases where there is a net force tending to translate the body, then in the direction of that acceleration, that normal force is likely to get shifted. The maximum to which it can get shifted is the edge. That is what we have learned. Okay? Right. But since in most of the cases, I'm not going to represent any complications, I would only take up cases for normal force. Okay? Now, with this background, what is normal force? Whenever two bodies are pressed against each other, the force exerted by one on the other is called normal force. And it is always perpendicular to the common surface or interface. And this is one so-called normal component of total contact force. You may also call it as normal component of contact force. That way also you may call it, if normal you are talking, what is tangential? That we will discuss in the next case, friction. Okay? Now, with this, let me take example one after the other. In the process, I keep on applying Newton's second law, and I'll show you in how many ways this normal force expression differs. So, never be under wrong impressions that n is such and such a value, etc. Let us start with the most simple case of all. This is N, this is mg, N is equal to mg. N is equal to mg. Okay? Now, if I am applying a force F there, this is mg. Here also, N is equal to mg. No difference at all. Only thing is N gets shifted a point I have already told you before. Now, this is a fixed surface. I am pushing this with horizontally. This is a contact, and we know that this is mg. So normal force will be like this, and m is equal to F. The body is not in equilibrium, so while pressing, if it is more, it is bound to accelerate down with the g. So mg in fact should be equal to ma. It should fall. Okay. Since I am worried about normal force, I am giving it to you like this. Now, for example, here is a vertical surface. This itself is accelerating with a. I am placing a body here. Now you see, when you go in a scooter, you take a paper and you drive, you keep it here. If you keep it here, generally it will fall. But when you go in a scooter, as long as you accelerate, the body will remain here because it's a very light body. So, what happens here? If I keep a body, what are all the forces in the frame of this? I told you, whenever the frame itself accelerates, you have a technique called pseudo force to use it. So I'm using it here. This is N, and pseudo force opposite to the direction of acceleration, and it is nothing but mass times acceleration. So N is equal to ma here. That's one way. The other way, the only force acting here is N. Now they may ask you to draw FBD in inertial frame. Then you should not write pseudo force. Okay? So N is equal to ma. You got this point? Right. So I've taken a vertical surface moving, vertical surface fixed, horizontal moving we have seen. Okay? Now I go to the surface, horizontal. Suppose I am applying a force. This is called, you are pushing the body at an angle alpha with horizontal. Alright? Now, what are the components? F cos alpha, and this is F sin alpha, this is mg, this is m. How do you write now? What are the upward forces here? N. Okay? Downward forces, minus mg because downward, and minus F sin alpha. Does the body accelerate up or down? No. Therefore, it is net force is 0, or N is equal to mg plus, this is what we call as push. Now we are entering a very important sector. Same horizontal force, no complications. Only thing is I'm pushing the body at an angle with the horizontal, and when you push it, you see the normal force, what could have been mg, is now increased to mg plus f sine alpha. Very important, remember. Now, if I take a pulling force, this is pulling. So what do you get? Mg n f cos alpha f sine alpha. How do you write that? In the vertical, n upwards, f sine alpha upwards, n plus f sine alpha minus mg is equal to 0, or n is equal to mg minus f sine alpha. That is pulling. If a question is asked, when the body is pulled, normal force decreases. Is it true? You cannot give an answer to that. Is that pulling taking place at an angle with the horizontal or not, an angle with the direction of motion or not? Then only we can talk about it. Just because I say pulling, you can't say it is reduced. Here, look at this. Push, pull makes no difference. But here it makes hell of a difference. So angular, at an angle, pushing leads to increase in normal force. At an angle, pulling leads to decrease in normal force. All right? Now you have seen a pushing case, pulling case. In the horizontal, same thing we can see even in the vertical. Suppose I'm pushing the body. This is F cos alpha. This is F sine alpha. This is normal force. That is mg. Got the point? Now, what is normal force here? N, it's not moving. N is equal to F cos alpha. You got the point? And here, of course, G plus F sine alpha will have an acceleration. I'm not going into that at this stage. I hope this point is clear to you. Okay. Right. Now, we have seen these surfaces. Sometimes, if I take a curved surfaces, remember, I never discussed dynamics of circular motion. I discussed only kinematics of circular motion. What did we learn from there? It always says that there is a centripetal acceleration directed towards the center compulsory, whose value is, at that instant, it is v square by r. Okay? Now, in this context, probably, I can define whenever a body is moving in a curvilinear path, the net force acting on the body in the plane of motion towards the center is called centripetal force. I'm introducing a very new concept of forces. This doesn't figure in our original forces. No. You have electromagnetic forces, you have gravitational forces, you have strong forces, and in electromagnetic or electroweak force, you have tension, normal force, frictional force, spring force, but CPF doesn't find a place there. Why? CPF is a net for any force, gravitational, electromagnetic, strong, anything. It is a combination of one or more real forces. It's a combination of one or more real forces acting on the body, same from here till here. That is called centrifugal force. Now this is a very important point. Tension alone could be CPF. Actually, the net force acting in the plane towards the center is reconstrained as centrifugal force. A new name is given to the existing set of forces. Centrifugal force is not a new force. Whatever forces you are talking, if it goes in this way, we will call it as centrifugal force. That's all. Tension alone could be centrifugal force. Gravity alone could be centrifugal force. Normal force alone could be centrifugal force. Combination of normal gravity, normal friction, or spring tension, anything could be centrifugal force. But never take centrifugal force as a separate force. It's a set of combination of one or more real forces only. So what is centrifugal force? You always give an answer based on the diagram, complete the circle towards the center, draw the forces, get the components and see what is acting towards the center. That all that you algebraically add up, and that will give you the centrifugal force. That's how you have to understand centrifugal force. Now, suppose you have on a body, you have got sigma f towards center is CPF, and CPF by Newton's second law is always equated to MAR, radial acceleration, or mr omega square or mv square by r. Be very careful. Neither mr omega square is a force, nor mv square by r is a force, but on left hand side all are forces. Now sigma f is equal to ma. Is ma a force? No. So this is important. Now Newton's second law, what does it say? Sigma f is equal to ma. What is a? Acceleration of the body. And what is v? A velocity of the body. And what is omega? Angular velocity of the body, right? So MAB, mv square by r, these are never called forces. Then what are they? They are the consequences of the forces. It's a consequence of all the forces. And what will happen if all the forces act? Your answer must be it accelerates the body. And what is that acceleration? You may find out from this equation and say that all the forces are on the left hand side and the acceleration is on the right hand side. So the definition of acceleration is the net force acting on the body per unit mass. We have a tendency to give acceleration as rate of change of velocity is known. That is a way to calculate acceleration. The definition of acceleration is net force acting on the body per unit mass of the body. That is what we call as acceleration. Okay. Now, if you recall, this is one part of the story. When you took sigma f is equal to ma, this is all set of real forces. I told you, it is all set of real forces. Now, suppose if I apply this in a non-inertial frame. Now, follow, my friends, carefully you have to look at it. When you take non-inertial forces, I told you to introduce an imaginary force, inertial force, fictitious force. I told you it is only a way to work out the problem. It is not necessary for you to do that. You can still work out the problem. But the technique also, I am telling you, it is only a technique and nothing else. I already made a mention in my previous lecture. The way we were using X in our childhood, the way you use your curry leaves in all the items, at the end of it you throw it off. In a similar way, at the end of it I'll throw off this and get my final answer and say this is the acceleration of the body. Now, if acceleration of the system is as, what is the imaginary force acting? Presumed to act on the body minus ma, opposite direction, right? So, sigma f real plus, what is that force you are doing? Opposite. So, I am putting it minus m. Now, if you use inertial force like this, I already told you, you will get only relative acceleration. Please understand this and don't write sigma f is equal to ma. What is that a? You have to understand. If you have to write a properly, you should know what is your f. If you f for all real, you will get absolute acceleration. If on the left hand side is a combination of real and imaginary forces or only imaginary forces, then the right hand side will give you mass into acceleration of the body with respect to system only you will get. And in this case I called minus ms. This is a force presumed to act on the body. Right? There is no name given to this. This is when the body is moving in a straight line. So this is the pseudo force that you can think of. Okay? Fine. So ma is not a force unless you take all these criteria. Is MABS a force? Never. Minus MAS, it is an imaginary force. Okay? Right. Now, with this background, I presume that there is a body moving in a curvilinear path. Then what will happen? Here, centripetal force must act towards the center. You go here or you go there, wherever you go. Okay? Now, the centripetal force is equated to mr omega square or mv square by r. Even here also, supposing, don't write CPF here. All forces you plot and then say, for example, I am having this on this. So this is mg, this is n, this is moving with certain velocity v. What is the centripetal force here? What will be your answer? Net force along the radius you see. Along the radius it is mg, opposite that is minus. So mg minus n is your CPF. And then CPF is always equated to mv square by r. So you can find out what is n. That's it. got my point? What is that centripetal force you are looking at here is, what is centripetal force? Never give your answer as m r omega square or mv square. Are absolutely wrong. Centripetal force could be a combination of the actual forces. Now, can I apply an inertial force here also, much similar to what I did in the case of your straight line motion? Yes, you can. Centripetal force will act like this. So, opposite to this is what we call as centrifugal force. Centrifugal force. And what is this? Centripetal force, which will act towards the center. What is mv square by r? Acting, presumed to act away from the body. So, it is m into as minus, so opposite to this x. There is an acceleration in this direction. But now you are taking in the frame of reference of the body. Therefore, I can imagine a fictitious force mv square by r. And then if I do that, what I will get is a relative acceleration only. So what do we do here? N, this is M, the same problem as before. Now there is no relative motion of the body with respect to that. Therefore, the net acceleration here is 0. So how do I write? Or what is N? N is mg minus. Now here also you can put N is mg minus. Answer will be the same, my dear friends. How you get it, that's it. What is the difference between the way you do this problem and the way we did this problem? The way we do this problem is we look at only absolute forces and we have taken them and equated them to mv square by r. And here I am using a concept of inertial force. Incidentally, this is given a name, whereas minus MAS is not given a name. So, that name centrifugal force, many people wrongly think that CPF is action, CFF is a reaction. This is absolutely wrong. Why? Action reaction should never act on the same body. First point. So CPF is acting on the body. Your so-called centrifugal force is also presumed to act on the body. So how can you call it as reaction? No. Then do you have a reactionary force of centripetal force? Yes. That is called centrifugal reaction. The total force by the body in the line of radius away from the center, that is called centrifugal reaction. Action, reaction. CFF is our introduction. We introduced this. We have introduced that. It is just used for the sake of convenience and no other importance need be attached to this. In fact, you can do the problem without CFF also. Sometimes it becomes easy, but in the process, never get confused. Both are real. This is purely imaginary. There is an action-reaction pair there. Here, for any pseudo force, no reaction. Remember that. Oh, what is a pseudo force? Any force that doesn't have a reaction is called a pseudo force. Likewise, you can say. Hope this is clear to you. Okay, I'll put a stop to this here.